Okay, let's dive right into this explainer. Today, we're going after the absolute holy grail of distributed systems engineering, building true fault tolerance and hitting that legendary exactly once stream processing. We're going to unpack exactly how massive, modern data systems handle constant, everyday chaos, yet somehow manage to spit out the correct answer every single time. To really grasp the stakes here, just picture this total nightmare scenario. You're buying an incredibly expensive plane ticket, right? You click pay, the little loading spinner starts, the network request goes out, and the exact server node handling your transaction just drops dead. Literally, that millisecond. So what happens to your money? Did the payment actually go through before the server died? Did it fail? If your banking app automatically retries, are you about to get charged twice? It's terrifying. And that terrifying unknown? That is exactly where fault tolerance enters the chat. In the incredibly messy reality of physical hardware, fault tolerance doesn't mean magically preventing failures. That's impossible. It simply means your system anticipates these sudden breakages and is explicitly engineered to keep functioning correctly anyway. It's all about surviving the chaos gracefully. Because here is the hard, unavoidable truth of distributed architectures. Partial failures aren't just possible, they are absolutely guaranteed to happen. We're not talking about some rare, once-in-a-decade anomaly. We're talking about standard Tuesday stuff. Network connections drop. Packets get delayed infinitely. Entire server racks lose power. You hit silent disk bugs. And of course, those notorious stop-the-world garbage collection pauses that completely freeze a node, making it look completely dead to the rest of the cluster. So when dealing with these inevitable breakages, engineers basically have a menu of 3 processing guarantees to choose from. First up is at most once. This is the fire and forget approach. We send a message, we never retry it. Sure, it prevents duplicates, but data loss is highly, highly probable. Second is at least once. Here, we aggressively retry the operation until we get a success confirmation. Great, no data gets lost, but it totally opens the door to processing the exact same message twice. And finally, the absolute dream, exactly once. No data lost, and absolutely no duplicates created. 0. But why is pulling off exactly once so ridiculously hard? Well, it all boils down to something we call the network black hole. The fundamental conflict in any distributed system is this. If your network request times out, you have absolutely no clue what happened on the other end. Did your request completely fail to reach the server? Or did the server process your payment perfectly, but the success response simply got swallowed by the network on its way back to you? You literally cannot know. Now, if you opt for that at least once guarantee and just aggressively retry a failed message to prevent data loss, you can trigger a catastrophe of duplicates, unless your operations are fundamentally designed to handle it. Think about the difference between a non-idempotent action, like add $10 to my balance, versus an idempotent action, like set my balance to exactly $50. If a network timeout causes you to retry that first action 3 times, congratulations, you just accidentally credited $30 instead of $10. That's a huge problem. And that right there perfectly illustrates the crucial need for idempotency. An idempotence operation is simply one that you can safely execute over and over and over again, but the final result never changes after that very first application. It's basically the engineering equivalent of hitting an elevator button. You can stand there and impatiently smash that button 5 times in a row, but you're still only getting one elevator car. Now, taking all of this and applying it to continuous data streams adds a massive layer of complexity. In old-school batch processing, if a daily job fails, no big deal. You throw away the corrupted output and just run the file again from scratch. But streams never end. They run continuously for months, even years. We absolutely cannot wait for a streaming job to finish before we make its output visible, because by definition, it literally never finishes. So, instead of throwing everything away and starting over, modern stream processors rely on durable logs. Message brokers take incoming events and append them to a continuous, durable log written straight to disk. Consumers then read these events sequentially, and they track their exact reading position using a specific marker known as an offset. You can think of this offset exactly like a bookmark in a never-ending novel. You always know exactly where you left off. But to survive a crash without having to reread the entire novel from page 1, stream processors also have to periodically save their in-memory computations. They typically pull this off in 2 ways. There's micro-batching, which chops the infinite stream into tiny, rapid-fire 1-second batch jobs. Or there's checkpointing, where the system periodically writes the operator's exact state to durable storage, usually triggered by special barrier markers flowing through the message stream. Whichever method, these essentially act as save states for your data. And these save states are what allow us to build a totally rock-solid recovery flow. When a processing node inevitably crashes, and it will, the system doesn't panic. A brand new replacement node simply wakes up, loads that latest durable checkpoint to completely restore its memory state, and then looks at the log to sequentially replay the messages starting from its last known offset. It seamlessly picks up exactly where the dead node left off. So here's the big secret. Exactly once semantics is really a bit of a magic trick. It's an illusion. Under the hood, your system almost certainly crashed, recovered, and retried the work. It processed the data at least once, but because of how meticulously we engineered the state, the offsets, and that recovery flow, the final effects of that computation are tightly controlled, so they only actually happen once. Honestly, a much better name for it is effectively once. We pull off this powerful illusion of correctness by combining those replay mechanics with some truly rigorous output management. This means we have to immediately discard any partial output from failed tasks. We use atomic commits so that database writes happen all or nothing, no half-written junk. We explicitly include the stream message offset right there in our database updates, so we know without a doubt what we've already processed. And we strictly suppress any duplicate messages using end-to-end unique request IDs. Let's bring this all together and apply these abstract concepts to a real-world, incredibly high-stakes scenario. Safely processing a financial transfer from account A to account B. We have got to ensure that this money moves safely without ever accidentally double charging the person paying, even if somebody unplugs our data center halfway through. If our stream processor attempts to directly write a debit to account A and then a credit to account B in 2 totally separate steps, a crash exactly in between those steps utterly destroys our data integrity. The money is literally missing forever. So instead, we use logged requests. We write a single atomic intent message straight to our stream log first. Once that one intent is safely and durably logged, we can reliably derive all the downstream account updates without any fear of half-finished operations. So here is what that bulletproof stream processing flow actually looks like. First, the client creates a payment request attached to a totally unique identifier. Next, that request is durably appended to the stream log. From there, the stream processor reads the log and emits the specific calculated debit and credit instructions. And finally, the downstream account databases deduplicate those incoming instructions using that unique ID. So even if the stream processor completely crashes, wakes up, and replays the log, those downstream databases will safely ignore the duplicate instructions because they instantly recognize that ID. The money is safe. To wrap up this explainer, I really want you to internalize a few core engineering truths. Number 1, distributed networks will lie to you and faults are absolutely guaranteed, designed for them from day one. Number 2, at least once processing is the industry standard, but it categorically requires item-potent endpoints. 3, your offsets and checkpoints are your system's save states. 4, replaying streams is the secret to true resilience. And finally, exactly once does not mean the machine never retries a task. It means you've designed your architecture so the final visible effects are perfectly correct. As you sit down to architect your very next data-intensive system, I want to leave you with a crucial question to ponder. When your application inevitably retries a failed operation, and it will, have you actually built true end-to-end idempotency to automatically suppress those duplicates? Or are you just crossing your fingers, deploying to production, and praying the network never blinks?